Okay, so in this online lecture, I'm going to be talking to you about a new topic. I'm going to introduce the thermodynamic identity, and we'll also be talking about entropy and fundamental definitions of temperature, pressure, and chemical potential. So let's put a title for this lecture is the thermodynamic identity, which turns out to be a particularly useful relationship that we'll use many times going forward in the course. We're going to talk about how this relates to entropy and fundamental definitions of a few different quantities: temperature, pressure, and chemical potential. Okay, so to start with, I'm going to introduce these quantities and these ideas in the context of an ideal gas. So the first thing I'm going to do is write down what we've looked at a couple times already, and that is the Sackur-Tetrode equation, which is an approximation for entropy of an ideal gas. So let's start with recall the Sackur-Tetrode equation. Which tells us the entropy for an ideal gas. So the entropy is approximately given by this relationship, log of volume divided by number of particles, pi u over 3n h squared. Okay, so that's the Sackur-Tetrode equation. So, so obviously this entropy of the ideal gas depends on a few quantities that we can change in an ideal gas. So we've talked about how it changes, how entropy changes if you change energy, and that's how we got to a fundamental definition of temperature. We'll revisit that in a few minutes here. But it also, we can talk about how entropy changes as you change, for instance, the number of particles in the gas, n, or as you change the volume of the gas, v, during compression or something like that. So let's just write that down explicitly. S depends on n, v, and u, the number of particles of volume or the energy of the gas. And it also depends on some other constants. So you could, other constants that we don't change. We don't have the ability to change the mass of the particles, h, Planck's constant, or pi, or Boltzmann constant. So we've got the mass, Boltzmann constant, pi, and h in here that we're not going to be concerned with. So we're going to be concerned with how entropy changes as you change these three different variables. So like I just mentioned, previously we came up with a definition of temperature based on how S depends on U, or how it depends on the energy, right? So temperature can be defined according to this relationship. This is the derivative of entropy with respect to U. It's actually the inverse of that. And that's a derivative that's taken with volume and number of particles held fixed. Right, so remember, when I write these little subscripts here, this means holding V and U fixed. Okay, so that's one thing we learned, is about temperature and how that is related to changes in entropy. So the next thing we're going to consider is what do we learn if we consider how entropy changes with volume, or how entropy can changes with number of particles, n. Okay, so that's sort of our goal, or part of our goal for this lecture is answering the question, what do we learn from these other derivatives of entropy, how it changes with volume, and the derivative telling us how entropy changes with number of particles. Okay. So we're going to first work on the ds dv one. So this is talking about how entropy changes with volume. Okay, so I'm going to leave this expression here. So we're going to take its derivative with respect to volume. But this is the question we're going to work on. Okay, so but before I take its derivative, I'm going to rewrite it slightly, as we often do. So I'm going to be taking a derivative with respect to volume. So I'm going to rewrite this natural log, splitting it apart, isolating the volume dependency from the other dependencies that we're not going to be taking, that are not going to be changing. So we have nk times log of v. And then if we split that logarithm up, the v is multiplied by a bunch of other stuff inside this logarithm. Oops, I forgot one of my parentheses there in the Sackur-Tetrode equation. Okay, so we have a 1 over n, and then we have this 4m pi u over 3n h squared to the 3/2. And then there's still this 5/2 sitting there. So that's just rewriting s. Now we can go ahead and take the derivative. So then the derivative of s with respect to v is a little simpler to see, because this doesn't depend on v, this doesn't depend on v. So the only term that depends on v is this first term here. So this is nk ddv of log v. Derivative of log v with respect to v is just 1 over v. So this is nk over v. Right? So when we take the derivative of entropy with respect to a change in volume, we get nk over v. Now, if we also remember, so the ideal gas law, we know, tells us that PV is equal to nkt. So nk over v, so this ideal gas law here implies that nk over v is equal to p over t, right? So you take the t to this side of the equation, the v to that side of the equation. What we find here is that ds dv, at least holding fixed n and u, remember I took this derivative just with respect to v as if the u and the number of particles n is not changing. So this is equal to pressure over temperature. And we can use this expression to come up with a sort of a definition of pressure. So we could rewrite this slightly and say that the pressure of this ideal gas is equal to temperature times this particular derivative. And that's a ds dv. Fixed n and fixed u. So this, similar to how we found a fundamental definition of temperature by considering changes of entropy with respect to energy, here we've got a fundamental definition of pressure by considering how entropy changes with volume, although this t is also multiplying that derivative. Okay, so that's one of the steps that I wanted to show you. The next step is going to be considering a derivative of entropy with respect to n, the number of particles. And that's where we're going to be seeing a new quantity appear, which is the chemical potential, which we haven't talked about yet in this course, although you may have seen it in various other courses in chemistry and so on. So let's. So I'm going to give you a little bit of a spoiler alert here, which is that what we're actually, so what do we get if we take the derivative of s with respect to n? Well, this is where the chemical potential comes from. So I'm just going to go ahead and write it down here. So chemical potential, which we give the symbol mu, is related to these definitions of to the derivatives of entropy as follows. It's minus the temperature times ds dn. And this is holding fixed the volume and the energy. Okay, so this is a fundamental definition of chemical potential that comes from these derivatives of s with respect to n. Let's go ahead and compute this derivative so we can learn a little bit more about what this means, what the chemical potential actually is telling us. Okay, so all right. Again, let me rewrite. I'm going to rewrite this a little bit so that we can more easily take this derivative with respect to n. Okay, so let's see. I'll do it in a couple of steps here. So like I just did before with volume, I'm going to isolate all of the n dependence within this logarithm argument and then separate the logarithm into two pieces. So log of, so in the n dependency here, we have a 1 over n right here, and we have a 1 over n to the 3/2 here. So we have a n to the minus 5/2. Let's see. Right, this is an n to the minus 1, this is an n to the minus 1.5. Together that's a minus n to the minus 5/2. Okay, and then again we can split the logarithm up such that the rest of the stuff that doesn't depend on n is left. So v times this 4 pi mu over 3h squared. That's everything except for these two n's here. And then we have the 5/2 sitting out here. Okay, so now let's take the derivative of this with respect to n. And again, this is a partial derivative, so we're keeping u and v fixed. Okay, so first thing is to note that, well actually let me just make one more note here. So again, if the properties of logarithms, we have n to the minus 5/2 here, so this thing can be rewritten as minus 5 over 2 times natural log n, right? So that makes things a little simpler, but let's go forward here. So we've got an n here multiplying everything inside the square brackets. So let's first, we're going to apply the product rule here, first doing the derivative on this term, and then we'll add to that the other part of the product term. So we have k times this minus 5 over 2 natural log n plus natural log of some stuff. This stuff here is this stuff. I'm not going to write it out. That's the first term in the product rule. And then we have the second term in the product rule is going to be nk times the derivative of the stuff inside the square brackets with respect to n. So that term is gone, that term will be gone, leaving only the derivative of this term with respect to n, which will give us a minus 5 over 2 times 1 over n. again, we're taking a derivative of log n. Its derivative is 1 over n. Okay, so note, let me see if I can get a different color here. We have well, this n cancels that n. So we have a minus 5 halves k here. And then we have this plus k times plus 5 halves here. So that cancels, right? This 5 halves k cancels with that minus 5 halves k, leaving us, so this one cancels with this term, leaving us just with this term. So we have a minus 5 halves k log n plus k log of stuff. That's the same stuff here that is independent of n. Okay. So now that we've taken the derivative with respect to n, I'm going to recombine these logarithms so we can see a little bit more about what this mu really is and what it depends on. So let me recombine these two logarithms now. And again, this guy I'm going to put it back together similarly to how we took it apart here. So let's put the 5 halves back as an exponent on the n. So we have k times natural log of n to the minus 5 halves. And then let's get this stuff that I represented by a swiggle back into this natural log. So that's a v times 4 pi m u over 3h squared. That's it. That's the stuff that was in the squiggle here. So close that square brackets. That's the argument of the natural log. Okay, so this thing is it's not looking that neat, but we're going to neaten it up with a few more steps here. So again, this n to the minus 5 halves, just like here, that n to the minus 5 halves can be divided up like this. So we have a k natural log of v over n. We can put this 4 pi m u 3h squared and put the n back in here. Oops. 3n. Okay. And I'm going to just take one more simplifying step, which is to rewrite this. So if you recall that u, so we're going to use this fact here, that u for an ideal gas, a monoatomic ideal gas, is 3/2 nkt. Right, that's the equal partition theorem for a monoatomic ideal gas, which is what the Sackur-Tetrode equation is for. Right, this is for monoatomic ideal gas. Then we can replace this u with this 3/2 nkt. It will cancel this n. Let me write it like this. So if we have a u over 3n, that's equal to kt over 2, just moving the 3 and the n to the denominator on this side. So in this piece here, we have a u over 3n that we can replace with a kt over 2. Okay, so then this guy is k natural log of v over n, which I'm going to relabel that at the moment. So let's call that v over n. I'm going to call it 1 over c. Okay, and why I'm calling it c is because n over v is the concentration of the gas particles. That is, it's the number of gas particles per volume, which is concentration, right? So this c here represents concentration of the gas particles. And let me finish writing this term with the substitution. So we have a 2 pi kt over h squared that's replacing this u over 3n by kt over 2. So this 4 got turned into a 2 because of the 1/2 here. Still to the 3/2 power there. Okay, so let me go back to here. So what we have then, so remember this is the result for ds dn. So if we want to write down what is mu, then mu is equal to minus t times ds dn. So this is ds dn. So we have k natural log of c to the minus 1, that's this 1 over c, and then some stuff that depends on temperature here. 2 pi kt over h squared to the 3/2. Okay, so we're almost to the point where I'm going to stop manipulating this. So this c to the minus 1, well, let me split this logarithm up again, as we like to do here. So we have plus t, so plus kt natural log of c minus kt, oops, minus kt times natural log of the 2 pi kt h squared to the 3/2. So we can put the 3/2 out here. Okay, so I did a couple of steps there. One of them, the first step was to split this log of this term times that term into a sum of 2 logs. And then in both cases, I took the exponent out front. So in this case, the exponent was a minus 1, which is why this is a plus. And this, for this term, the exponent was a 3/2, which is why this is a 3/2 multiplying this term. So this is an expression for the chemical potential for an ideal gas, monoatomic ideal gas. And the main thing I wanted to point out here, so since this chemical potential may be a new quantity for some of you to think about, I wanted to give you some intuition for what is it telling us. So at least for the moment, I want to point out that it's a quantity that goes up with concentration, so or density, depending on how you want to think about it. Remember, the C is defined as the number of particles per volume, right? That was the substitution I did between this step and this step. So if the number of particles per volume goes up, then the chemical potential goes up. So it's telling you something about how crowded the gas molecules are in the space that they're in. It's the density, it's the concentration. So if, and where this is going to become important is if you have two systems with different chemical potential, so for instance, two ideal gases with different concentrations, they will have a tendency to, through diffusion, or diffusion processes that lead to a diffusive equilibrium, concentrations will want to equalize, and mu will want to equalize. So I just want to make sure in this first presentation of chemical potential you see that it's closely related to the concentration of particles. That's one takeaway message for mu. The other thing is it's closely related to how the entropy changes as the number of particles in the system is either increased or decreased, right? That's this definition. So if the entropy goes up by adding a particle, then mu goes down because of this negative sign. Okay, and it also depends on temperature in a rather complicated way, right? We have a t multiplying this term, and then a minus t times some other things here. So the dependency of mu on temperature is more complicated. I just wanted to make sure it's clear that you see that mu goes up as the concentration goes up. Okay, and maybe just as a little bit of a preview of things to come later in the course, another way to understand mu that's somewhat simpler is when you start to think about free energy. So let me just write it down. I know you don't know this concept necessarily yet, but later we're going to come back to this So I'm just going to write it down now. Mu is also the free energy per particle or per molecule in the gas. So this is something we're going to come back to later in the course. Okay, so at this point, I'm done with the first part of the lecture where we're talking about how entropy changes with changing volume and with changing n. And through that process, we've introduced mu, the chemical potential, and a fundamental definition for pressure. Okay, so now I'm going to come back to this thermodynamic identity. So I'm going to introduce this topic of thermodynamic identity, which is closely related to what we've been talking about so far. Okay, so erase this. Okay, so and what we've been doing so far, I've been considering these changes in entropy due to changes in energy, volume, and number of particles. So one way to sort of generalize this is to, okay, so let's write this down more generally. A small change in entropy let's call it ds. It can be thought of as due to 3 different possible ways that entropy can change. And I'm basically going to be writing down, using the chain rule, to write down the following expression. So you can say ds du times du plus ds dv times dv plus ds dn dn, right? That's just chain rule, sort of basic calculus. Now, again, these partial derivatives sort of mean this, but we add these subscripts to make sure it's very clear that this derivative is taken with n and v fixed, this derivative is taken with u and n fixed, this one is taken with u and v fixed. Okay, so a general change in entropy, even if, well, can be thought of as comprised of these 3 different possible ways that the entropy can change. Okay, so now if we replace each of these partial derivatives with their related quantities, in this case this is 1 over temperature times du. In this case, this was what we just showed was pressure divided by temperature times dV. And then this term is related to minus sign here, related to the chemical potential mu divided by temperature. Right? So this is a general expression for how does entropy change if there's some small change in energy, volume, and number of particles when the system is at a particular temperature, pressure, and chemical potential. Right? Now, if we rearrange this equation slightly, then we get to what is called the thermodynamic identity. So let's solve this for du. Right? So first thing is to multiply everything through by temperature. So we get T ds, and then minus P dV plus mu dN. So that's just solving this expression for du. Right? You multiply through by temperature, and then move the P dV to that side and the mu dN to that side, and there you have it. So this expression is called the thermodynamic identity. Okay, and one of the main things I want to point out, even though everything I've done in this lecture so far was in the context of ideal gases, this expression is in fact more general than ideal gases. This applies for a wide range of systems, including liquids, and in some ways it applies to solids. So this expression is not limited to ideal gases. So make a note that this is in fact a very general expression. More general than ideal gas. It applies to other situations as well, even though the derivations that I did for temperature, pressure, and mu were in the context of the Sackur-Tetrode equation, which is an ideal for ideal gases and not for any other system. This expression could be derived for other systems as well, is one way to see it. Okay, so I think that's where I'm going to stop for this segment of the lecture, and we'll have another segment